Hey guys, welcome to the 7th episode of the AI series. In today's video, we're going to take a look at how do we train and test our model. So let's get straight into it. The last video gave us a golden rule. Never judge a model on the data trained on. You have to test it on data it's never seen. Today we put that into code, line by line. We'll load a real dataset, split it on a training half and a hidden testing half, train a model, and measure how well it does on the part it never saw. And I'll explain exactly what every line is doing along the way. Now, in the first cell, this is just our inputs, which we also did last video. From sklearn.datasets, import load iris. Scikit-Learn ships with practice datasets built right in the library. From its datasets section, we grab load iris, a function that hands us the famous iris flower dataset. So we don't really have to even download a file. From sklearn.model selection, import train test split. From the model selection section, we take train test split, the tool that cuts our data into a training part and a testing part. That is the main point of today's video. Then the next line, from sklearn.neighbors, import kneighbors classifier. Our model, k-nearest neighbors, lives in the neighbor section. I'll be honest that today it's mostly a black box. It classifies something by looking at the most similar examples it has seen. And it's going to earn its entire video later in the series. And the next line, from sklearn.metrics, import accuracy score. And from the metrics section, we're going to import accuracy score, the function that will grade our model's predictions. Now that we run it, let's move on to the next cell. The next line is iris is equal to load iris. We call the function with empty parentheses, and it hands back a bundle containing the measurements, the answers, and some descriptions. We store all of it in a variable called as iris. Then the next line, as we saw in the last coding video, x is equal to iris.data. Iris.data is a table of measurements, 4 per flower. We pull it into capital X, which is our inputs. Then the next line, y, is our output or our target. And iris.target is the list of correct species for each flower, written as numbers. That's lowercase y, which is our answers. Then the next line is print feature shape colon then comma x.shape. Dot shape reports the size of the data, how many rows and columns, and printing it confirms 150 flowers, each with 4 measurements. Then the next line is print classes, iris.target names. Target names are the human readable species names. Printing them shows the 3 types, setosa, versicolor, and virginica. 3 categories means this is a classification problem. Then the next line. The first line is quite long, but this single line is also very important. So let's go carefully. Train test split hands back 4 things at once. And on the left, we unpack them into 4 variables in the exact order: the training inputs, the testing inputs, the training answers, and the testing answers. That order is fixed by the function, so we must memorize it. Then inside the brackets, we have x and y. The first 2 things we pass in are the data we want to split, our features x and our labels y. Then we have the test size is equal to 0.2. This tells it to set aside 20% of the data as the test set. The remaining 80% becomes the training set. Then we have the random state is equal to 42. The split is random. It shuffles the flowers first, so we get a fair mix. Random state pins that randomness to a fixed value. Any number works. I use 42 just so that you get the exact same split I do and your numbers match mine. In the next line, we're going to print the training examples, which counts how many items are in something. we print the size of the training set, which is 120 flowers. And in the next line, we print the testing set. And the test set is 30 flowers, sealed away that the model will not see while it learns. And when you run it, we get training examples 120 and testing examples 30. In the next line, we are going to train the model. The model is k nearest neighbors classifier. We create the model, the setting where we set the neighbors is equal to 3. Tells it to look at the 3 closest examples when it makes a decision. Don't worry about the number today. When we discuss this type of classification in detail, you'll understand it. And the next line, we put model.fit xtrain ytrain. The same .fit command as before, but look carefully at what we handed. We handed the training data only. 30 test flowers appear nowhere here. The model studies purely from the training set, exactly as the rule demands. And when we run it, we get the same box as before, but this time it's for k neighbors classifier. Now, in cell 5, the first line, predictions is equal to model.predict xtest. Now for the moment of truth, we ask the trained model to predict the species for xtest, the 30 flowers it has never seen, and we store all its guesses in a variable called as predictions. In the next line, we just type the variable name so that it displays it. And when we run it, you will see an array of numbers, and each one is the model's predicted species for one test flower. But raw guesses don't mean much until we check them against the real answers. Now in cell 6, we are going to measure the accuracy. In the first line, test accuracy is equal to blah blah blah. Accuracy score takes two things: the true answers, y-test, and the model's guesses, which is stored in the variable predictions. It compares them and returns the fraction it got right. We store that as test accuracy. The next thing is training accuracy. So we do the same thing on the training data to see how it did on flowers it actually studied. The true training answers, y-train, against its predictions on the training inputs. The next line is where we print it. The 2% is the 2% is format code doing two jobs at once. It turns the number into a percentage and it rounds it to 2 decimal places. Then the next line prints the test score, and it is exactly lined up underneath. Now, when we run it, we want to compare the two. They are both high and close together, and that's exactly what we want. Both strong and similar means the model generally learned the pattern and generalized. If training was near perfect, let's say if training was 100%, but the test is somewhere 70%, we can confidently say that overfitting happened in this model, as we discussed in the previous video, where we said that if the training accuracy is high, but the testing accuracy is low, we are pretty confident that the model just memorized the data instead of generalizing with it. And that is called as overfitting. If this video helped you understand how you can train and test your model, then make sure to subscribe and hit the like button for more videos like this.